Hello friends, good afternoon and welcome to your Reset Live Lectures. Dear friends, as you know that we've started a series on coordination chemistry and today we're conducting yet another lecture in the same series. In today's lecture, we will be talking about molecular orbital theory of the coordination compounds. To discuss this topic, we have with us our subject expert Dr. Ajay Kumar Bhagi. Dr. Bhagi is Associate Professor in the Department of Chemistry in Dal Singh College, University of Delhi. Without further ado, I would like to welcome sir to our studios and request him to start the lecture. Welcome, sir.
Thank you very much. We had been dealing with this topic quite in detail, and we have discussed various theories that deals with the coordination compounds. And in fact, first of all, I would like to again highlight what is the importance of various theories which are being proposed for any type of compounds to explain their nature. In fact, there are various models and theories which have come up to explain the chemical bonding nature. And in fact, to understand the strength of a chemical bond and the nature of a chemical bond, and therefore ultimately that decides the properties of a compound, we must know the details or inside of the what sort of interactions between the central atom and the ligands that take place. And by now what we have done is we have covered some of these theories. Firstly, the Werner theory, which tells us about the composition of a coordination compound. It may have some failures, but we can't really ignore this theory as such, because many things about the composition of any coordination compound, what is outside the coordination sphere, what is inside the coordination sphere, has been discussed through this theory. And this becomes a fundamental of a new branch of chemistry that is called coordination compounds. Now in this, thereafter, many other theories were proposed so as to explain the nature of chemical bond, that means what sort of interaction that helps in holding the metal and the ligands together. And to explain the molecular shape or the complex ion shape, we have gone into this series to discuss the valence bond theory. Valence bond theory in itself also has some advantages, that it has been able to explain the observed molecular shapes or the geometries of various compounds that will help us once again to understand its properties in detail, and tailor-made compounds therefore can be made which can be used by the mankind to improve our lifestyle. Now, in continuation, we have seen that there were certain problems with the valence bond theory which couldn't be answered through the valence bond theory, like color of a complex and the magnetic behavior. To explain or have to have a greater insight into the nature of these compounds, in addition to the valence bond theory, a newer model based upon the electrostatic interaction that was being proposed based upon the crystal field theory. Now that is, crystal field theory has helped us to understand the observed color of various compounds, the spectra of the compounds, the magnetic behavior of the compounds. We have also been able to explain many other properties, that the variation of hydration energy, lattice energy, because of in the different ionic compounds formed by the transition metals. And that has helped us to in a great deal to understand the nature. Now, along with this, we also need to have a more quantitative approach. That is what you call is the molecular orbital theory. I shall repeat here that these theories are more or less complementary to each other. That means some information that we draw from the valence bond theory we may not be able to draw it from the crystal field theory. Similarly, the kind of room that molecular orbital theory will provide for having a greater quantitative aspects of the coordination compounds, it will allow the electron cloud overlap model to be existing, not as it was being found to be correct if you consider the crystal field theory. So all these things we'll be discussing together. So in fact, what we want to emphasize here is that they are not simple improvement of one theory of the improvement of the another, but in fact they are able to complement each other in a very well mannered, so that we have a full details about a coordination compound, and therefore we can use it the way we want. Now, to have just a sort of a information that what actually makes us to have the MO2 theory being also being proposed for the coordination compound. Now, in fact, we'll just like to revise here what CFT has done. And during the CFT, we considered metal ion and the ligand as point charges, and according to the CFT, therefore, the metal d orbital with respect to energy as a result of electrostatic effect has undergone a splitting. That means the d energy levels, d sub-level energy levels orbitals, they have undergone and to have the different energies. Now, CFT also leaves a little scope for covalent bonding. Now, this is one drawback that we want to answer, because here it is more important to us to understand that if you look at the exact energy parameters of the metal and the ligand bond, we will appreciate that this energy is just parallel to what covalent bonding is all about. Now, of course, the ligand here may be donating a pair of electron to the metal, but after the bond formation, the bond that has formed is covalent in nature if you go by energy wise. Similarly, spectrochemical series can also be explained, cannot be explained on the basis of point charge model. As neutral ligand like carbon monoxide is stronger than the chai ligand like halides. Now, this is something that we have encountered, and we know that if you have the negative chai ligand, if we go by the point charge model, in such a case, they should enforce a greater crystal field force on the metal so as to have a greater variation in the energies of the d orbital. But that has not been encountered. In the spectrochemical series, what we have found is that the neutral carbon monoxide type of a ligand also imposes a greater field strength. That means it is acting as a stronger ligand. Therefore, unless we shift our focus from the point charge model to a stronger bond formation between the ligand and the metal model, we will not be able to explain what has been exactly observed in the spectrochemical series. And therefore, we need to have a theory which allows some kind of a orbital overlap between the metal and the ligand. Now, this exactly that we have tried to do by adjusting the crystal field theory and then naming it as a ligand field theory. Now, to have a better understanding of what type of overlapping is taking place, which orbitals in fact overlap so as to form the newer orbitals where the electrons can reside, that can be dealt more easily and more comparatively better way in the molecular orbital theory. There is one effect which is always being talked about whenever we want to shift from the crystal field model to the molecular orbital theory, and that we call it as Nephelauxetic effect. Now, what this Nephelauxetic effect is? The energy calculations have shown that electron-electron repulsion in complexes are somewhat less than in the free metal ion. What it actually means is that if we calculate the energy of electron-electron repulsion term in a free ion, they are somewhat larger when it is in a bonded state. That means when it has undergone a complexation. Now, to what way we can explain this change in energy when a complexation has taken place or when it was simply a free ion? Now, for this, it is being attributed to somehow the electron density must be getting a larger space. That means now the electron density which was confined to a smaller volume of the pure metal atomic orbitals, now they are getting a chance to have a larger volume being to occupy the space, and therefore the electron repulsions must have reduced. Now, this in a way therefore tells us or gives indirect evidence that atomic orbitals during complexation must have formed some kind of a larger volumed orbitals, which later we call them as molecular orbitals. Therefore, the concept of AOs cannot be restricted to explain the complexation. The AOs must have undergone some kind of a larger volume sizes because of the overlapping of the metal and the d orbital with the ligand orbitals. Now the newer MOs, they will be bigger in size, therefore they can have, and remember, each orbital is going to accommodate maximum of the 2 electrons. So with the size getting expanded, the expected repulsions in complexation between the electrons is going to be reduced considerably, and that actually being gauged or measured in terms of the energy calculations. Now, ligands therefore allowing delocalization of d electron density of the metal to a larger volume, that what we call is the Nephelauxetic effect. In fact, Nephelauxetic means electron cloud expanding or cloud expanding in fact. So here we are talking about electrons. So electrons have undergone expanding, and that is being possible because of the molecular orbital being formed by the ligand and the metal overlap. Now this is a sort of a series I am showing in a tabular form, that this is a sort of a series that is called Nephelauxetic series for some of the metal ions and the ligands. Here some ligands, they are being given as representative ligands. You can very well see from here if their cloud expanding is being measured in terms of H and for any metal in terms of K, the Nephelauxetic effect will be proportional to the product of the two. Now, if you have a bigger size iodide, the H value is larger, that means Nephelauxetic effect would be larger. If you have a metal ion from a 3D, instead of a 3D, 4D or a 5D series, again the values are larger for the value of K. So K of the metal or H of the metal when increases, the product increases, so the Nephelauxetic effect increases. That means it is allowing more electron cloud expansion when such a ligand or such a metal ion is involved. So therefore, this electron cloud expansion and the ease for electrons in terms of electron-electron repulsion can also be measured in terms of the product of Hx and Km values, although here we have only given some representative values, but such a values, the value of H for various ligands can be calculated, the value of K also can be calculated for various ligands, and hence that will help us to understand how electron cloud expanding is being observed during complexation, allowing us to have an idea why there should be a covalent bond between the metal and the ligand, and why there should be a need to have a full treatment of molecular orbital theory so as to explain the exact nature of bonding and exact nature of what sort of energy parameters are undergoing change during complexation. Now, let us then first of all have a comparison of CFT and the molecular orbital theory. At the outset, I would like to mention here that as far as the properties such as color and the magnetic properties that we have talked about in the CFT, which could be explained for most of the complexes, the similar results would be obtained from the molecular orbital theory. Then what is the difference? The difference is here we are allowing the covalent nature of bond to be considered and the strength of bond to be considered as a prominent factor in deciding the energy of various atomic orbitals of the metal that undergoes an overlap with the electron density of the ligand. Now, it is not always necessary that the AOs of the metal which are undergoing the complexation or undergoing the overlap so as to form a bond with the ligand, they need to be always occupied. They may be empty orbitals, they may be filled orbitals, but that we have to see based upon their symmetry and the size and the energy consideration, that what sort of AOs from the metal and what type of the orbitals of the ligand they can undergo overlap so as to form the bonds. One difference which is very prominent if you are comparing CFT with the MOT is that MOT seems to be more precise in energy calculations. That means quantitatively it is far better than CFT. The reason being that we do not only consider the d orbitals of the metal here, we do consider the s, p and other orbitals that are also undergoing a change in energy when complexation takes place. That means when the ligand approaches the metal, we cannot selectively say that it is only the d orbitals which is undergoing the energy change, but there is no energy change for s and the p even in the valence shell. They all orbitals are there in the valence shell, and they all are there to accommodate the electron density which is coming from the ligand. So we have to consider this model as a more refined, better quantitative method or a model so as to explain the bonding between the metal and the ligand. Now consider here a ligand, that L having one electron pair which is forming a bond with the metal ion M+, having two sp hybrid orbitals, and in the metal there is only a single electron in the valence shell. Now when this happens, we say metal ion having complexed with L so as to form a Ml+. Now we will like to treat this complex from both the models. That means we will make a CFT considerations that what energy changes would take place if we consider this complex formation, a simple complex, a metal ion with the sp hybrid orbitals, 2 in number, then a ligand with the electron pair. It is going to form a bond between the two. These two are going to form a complex, like simple complex Ml, and this metal which we are considering, it is having only one electron in the valence shell. So if we treat it with the CFT theory, so as per CFT, the two unperturbed metal orbitals of equal energy which were degenerate levels, when it was in isolated state, they may split into two levels of energy under the influence of crystal field of the ligand, and they are separated by 10 dq energy. This is what we have learned. Whatever is the number of d orbitals or whatever is the number of hybrid orbitals which are there on the metal, when they are under the influence of a crystal field, that means that when the ligand is approaching, they are likely to undergo a split in energy based upon what sort of force that has been put by the ligand electron density onto the orbitals which are present on the metal. Now, based upon this, therefore, this simple energy level diagram for this particular complex can be drawn, where two are being separated by 10 dq value. That means two energy levels of the metal, two hybrid orbitals of the sp has undergone a change in energy, which two now atomic orbitals or the hybrid orbitals, they have separated by a 10 dq value, and one is of a lower energy than the other. This is the treatment as per the CFT. Now let us also then try to understand what happens if we consider the same complexation through the MOT. That will tell us the difference in approach for the two models. Now, if you go by the MOT theory, the ligand orbital can overlap with one of the sp hybrid orbital. Let us say the ligand is approaching from this side to this two sp hybrid. These are the two sp. One lobe is just designating one of the sp hybrid orbital. The second lobe is exhibiting or showing here the second lobe of sp hybrid orbital of the metal. Now let us say the ligand here from this side approaches the metal. So it is likely to affect the energy of this particular sp hybrid orbital. Now the ligand which is approaching to the metal, it is not necessary that it will have the same symmetry as that of the sp. If it has opposite, the energy would be increased. If it has same, energy would be lowered. Therefore, the interaction of a ligand with one of the sp hybrid orbital will result into a bonding MO and an anti-bonding MO that we have understood even for a simplest of the molecule treatment with MOT like hydrogen. A similar kind of thing is happening here. One is a destructive overlapping between the, when the symmetries are different, destructive overlapping between the sp hybrid orbital of the metal with the ligand. If they are opposite in symmetry, the energy is increased. If they are not, then the energy is decreased. Now let us look at that what actually is happening to the second hybrid orbital. In fact, since the ligand is approaching from one particular direction, so this direction, this particular hybrid orbital seems to be least affected, and therefore we say, since it is not taking part in bonding, this has resulted into a non-bonding MO. In short, as we have understood in molecular orbital theory, that the number of AOs or the hybrid orbitals, they are going to combine, they will produce equal number of MOs. What does it mean actually is that since there were two sp hybrid orbital of the metal with one of the metal, one of the ligand orbital. So in all there were three orbitals which are combining, so they will form three molecular orbitals, and that we'll see in the next diagram. See here. Now what has happened is this is unperturbed, unmixed metal orbitals. Let us say they have energy A1 and A2, they are being designated as these atomic orbitals, they are being designated as A1 and A2. This is the ligand atomic orbital. We'll later call it as LGO, but I'll just to refer it for the time being, we can call it as this is a ligand orbital. So this one ligand orbital is combining with two of them. This is the effect of charge. That means that is what we have understood in terms of CFT. Now, one of them which is away from the ligand direction, that is going to form the non-bonding MO, and the one which is towards that is going to experience a increase in energy, that is going to either constructively overlap or forming a bonding molecular orbital, and corresponding a non-bonding MO would also be formed. So two from here, one from here, three orbitals in total has resulted into three orbitals here, bonding AO. One because we call it as bonding, the one which has not undergone much change in energy and not participated in bonding is a sign, the which having opposite symmetry, therefore that is an anti-bonding MO. So this sort of model help us to distinguish. What we have been drawing by now was we were talking about only those ones which were getting interacted with, so only d orbitals undergoing a change. This sort of a equation now has changed here, and we are talking about all those orbitals which are there on the valence shell, what sort of energy changes they are undergoing when a complexation is taking place, if you are taking molecular orbital theory as a model so as to explain the complexation. Now, the CFT and the MOT model treatment, as I told you, may appear to be that they are very different from each other, but the results obtained by are qualitatively quite similar. For example, both says the odd electron, that the one electron which was there on the metal in the case that we have discussed, that must resides away from L. That means the ligand's electron. Unless it is so, if they are being forced to have occupying those, then the repulsion term would be larger. If there is a choice given, of course, the electron would like to have or try to occupy the orbital which is least repelled. So that means that becomes a lower in energy. And then we also have understood that the addition of 10 dq value or some amount of energy can promote an electron from one of the orbital which was directed away to one of the orbital which is directed towards the ligand. This difference in energy can also be understood that 10 dq is the energy which will allow electron to jump or to electron to shift from the orbitals which were away from the ligand to the orbitals which are towards ligand. And then the presence of odd electron in the later case would destabilize the molecule because the energy has been gained by the system. Therefore, destabilization in terms of energy has taken place. This therefore becomes an excited state of the molecule. And then you also know that the energy of transition of 10 dq is proportional to the extent of overlap. Now, we are not here talking about the earlier our presumption that what is the crystal field that is being forcing the d orbitals to have different energies. Now, what we are considering here is the metal in the ligand, stronger overlapping, stronger bond between the metal and the ligand will force to have a greater separation between the energy levels. That means the 10 dq would be larger. Now, this is how, therefore, we reach to almost similar qualitative results that can be obtained out of the two approaches. Although there is one strong benefit in terms of the molecular orbital theory, and that we have understood that it is going to benefit in terms of understanding that why a coordination compound should be taken as a bond between them to be taken as a covalent bond and not an ionic bond as proposed in the crystal field theory. Now, what actually we do whenever we want to apply the molecular orbital theory to various compounds. Normally, molecular orbital theory deals that it says that the AOs, they combine with the appropriate symmetry with a comparable energy so as to form the molecular orbitals. This becomes the fundamental postulate of the molecular orbital theory. When AOs, that means the atomic orbital wave functions, are combined, this is all the mathematical treatment that we do. When AOs combine so as to generate equal number of bonding, anti-bonding and non-bonding orbitals, we get a newer situation where the electrons then can reside in the molecule formed. And the bonding MOs are always lower in energy than that of the anti-bonding MO. These are the fundamental postulates that we always talk about for the molecular orbital theory. The electrons occupy the molecular orbitals in order of their increasing energy, and with the Aufbau principle, we can explain the same all principles that we have understood for filling of AOs are also applicable for the filling of MOs. And remember, the MOs are also going to accommodate at the maximum of 2 electrons as it was in case of AOs. So bond order is also, we know now this, that the electrons in the bonding MOs and the electrons in the anti-bonding MOs, if they are being subtracted from the bonding MOs and they are divided by 2, this tells us how many number of bonds that would be existing between the simple molecule. Now, let us then understand how actually this, though we are here dealing with more of a very qualitative approach at this point of time, we need not go into the exact energy calculations and calculations on finding out the newer wave function, the exact mathematical wave function. Mathematical treatment here is being avoided to understand the simplicity, or to make it very simple. It's a more of a qualitative approach of MOT that we'll be discussing for coordination compounds in the beginning. And therefore, what we normally therefore say that the molecular orbitals formed with the LCU of the metal, that means linear combination of atomic orbitals, that is a mathematical step that we carry out, that we write the wave function for the metal and the wave function for the ligands, and then we carry out certain mathematical operations so as to find the newer wave function. And the newer wave function of these orbitals combine in a constructive low energy bonding is formed, and if it is in a destructive manner, then it is a high energy anti-bonding situation that arises that we have seen. Now, going from the electrons from metal ions to the ligand fill the lowest energy, and the molecular orbital available to them, they can occupy those orbitals. So up to now, what we have done is we have understood what is the need of molecular orbital theory for explaining the coordination compounds. We have also understood or seen what sort of comparison is there in the two approaches of CFT and MOT, although qualitatively they are giving us the almost similar, identical results. Now, in the next session, we'll take up the complexation of particular type of compounds resulting into the what sort of energy level diagram that has resulted in through the molecular orbital theory. Thank you. Now, in this session, we will like to explain some simple complex, representative complex like octahedral and tetrahedral, and what sort of energy level diagram that we get because of the overlapping of the atomic orbitals of the metal with the orbitals accommodating the electron pair on the ligands, they are being more general referred as LGOs. Now, let us take an example of an octahedral complex and try to construct the molecular orbital energy level diagram based upon the molecular orbital theory. Now, for this, what we are doing here is that we have chosen a octahedral complex and we have presumed that it has formed 6 sigma bonds along the x, y and z direction as we did in case of CFT. Now, the ligands which will be approaching the metal along x, y, z, they are forming sigma, they are having a sigma symmetry orbitals, and therefore they can combine with dz square, dx square minus y square orbitals and not dxy, dxz and dyz. For the obvious reasons, because dz square, dx square minus y square, these two orbitals, they have their lobes in along the axis, whereas the other 3, that means dxy, dxz and dyz, they are having their lobes between the axes. So, ligand approaches along xyz axis forming a sigma orbital combined with only 2 of the d orbitals that we have seen. So, bonding and anti-bonding molecular orbital, if we are considering, they are to be resulted out of these 2. They are not being the part of the direction of approach of the ligand, therefore they will remain almost unperturbed, or maybe a little energy change that can take place, and therefore dxy, dxz, dyz, these d orbitals of the metal, they are going to form the non-bonding MOs. Now, some weak interaction will also take place, as I told you that we are not in isolation going to consider only the d orbitals. We on a metal ion have seen that in the valence shell, when there is a 3d, 4d or the 5d d orbitals are present, alongside you also have the 4s, 4p or 5s, 5p or 6s, 6p orbitals along with the n-1 d orbitals in the valence shell, if you are considering the transition metals forming a complex with the ligand. Now, therefore, what we have understood here is that on metal, the orbitals that we are going to consider will not only be restricted to only 5d orbitals, but along with this 5, there will be 1 of the s and 3 of the p. So, 4 s and p orbitals also along with the d orbital. So, in all, in the valence shell, there are 9 AOs, atomic orbitals, which we are going to consider that what energy changes they will be undergoing. Now, s orbital being spherical, so s orbital is also undergoing a overlap with the ligand that is coming. Px, Py, Pz. Now, the orientation of Px, Py, Pz is also along the axis. Therefore, the way dx square minus y square or dz square, these orbitals have undergone a overlap with the ligand orbitals. So, they will also can have some direct interaction with the ligand orbitals, and hence the energy change for s, px, py, pz cannot be ignored. So, in all, there will be 6 orbitals which will be undergoing a change in energy. 2 from the d, 1 from the s and 3 from the p. So, in all, there will be 6 orbitals, but there will be 3 orbitals which are not along the axis, dxy, dyz, dxz. They are the candidates so as to form, or say they are the candidates which are not going to be affected with the ligand orbitals force or overlap, and hence they are going to form a non-bonding situation. Now, this is the MO diagram that will show in the figure. Now, here we need to therefore understand that what actually has happened. These are the orbitals that we were referring belonging to the metal. Here is the 6 ligand orbitals. They may be having 6 pairs of electrons, so in all 12 electrons. Here, whatever can be the electronic configuration, there can be 1 electron in the d, 2, 3, 4, 5, depending upon which metal ion we are talking. Say for example, if you are talking about cobalt 3 ion, so there will be 6 electrons in the d of the atomic orbitals of the metal. So 6 here, 12 here electrons of the 6. Now let us see that what sort of combinations are possible. Now as we have discussed that the dxy, dyz, dxz, since it is forming a T2G set of orbitals, we have also seen it to be in case of CFT. So they are being unperturbed, their energy doesn't change, and therefore they are forming the non-bonding. Now all other 6, that means 2 of the D, 1 of the S, 4 of the P, these 6 orbitals will have constructive as well as destructive overlap with the 6 orbitals of the ligand. So in all 6 from here, 6 from here, 12 MOs would be formed. So when S combines with one of the ligand, it being spherical, the A1G symmetry results, and this A1G symmetry is only singly degenerate. Singly degenerate means there is only one orbital here, and a counter of it, that means when there is a constructive overlap, there will also a possibility of a destructive overlap between the two symmetries, and therefore A1G star also formed. So combination of 4s with one of the ligand orbital has resulted into 2 MOs, A1G and A1G star. Similarly, these 4p, we also understand 4p means px, py, pz, their lobe sign symmetries are different. One is on the plus, the other lobe is of the negative. So they are always ungeared type of orbitals. So these are being labeled therefore as first of the triply degenerate. So we put a symbol T here. This is the first in this series. So T1, and since it is ungeared, so we have written U. Now this T1U will also have to combine with the T1U set is also has to combine with the T1U of the ligands, so as to have one constructive, that means the bonding, triply degenerate bonding MOs and triply degenerate anti-bonding MOs. So in all, up till now, we have been able to see how 4 bonding MOs and 4 anti-bonding MOs are formed. Similarly, the dx square minus y square and dz square, they are being labeled as EG set of orbitals. This is doubly degenerate. Now remember, A actually, symbol A, B in spectroscopic terms, they are being taken for the atomic orbitals or the energy level, they are being taken as that whenever they are singly occupied. T term is being used whenever the energy levels are triply degenerate. Singly degenerate, triply degenerate, E is a symbol that we use for doubly degenerate orbital. So what therefore you get is, once again, a constructive and a destructive overlapping, identical symmetry overlap or a different symmetry overlap. 2 situations, in all 4 orbitals, 2 of them bonding, 2 of them anti-bonding, they are being formed. So in all, if you just see from here, 1 and 3, 4, 4 and 2, 6, 6 and 3, 9, and then here also you see 2 plus 1 plus 3. So in all, the number of AOs which were there here to combine, there were 9 in number, 6 here, so in all 15. So 15 MOs must be formed, and the order of increasing energy is also being ascertained. Now out of these 6 ligands, they are having 12 electrons. So first orbital will be filled, then this T1U is also being filled, and the EG is also being filled. So in all these first 6 of the MOs, they are likely to be filled with the electrons which are coming from the ligand itself. We do not know, in fact, it is not being seen, but we can take it as, since these 12 electrons are there, so 12 are going to at least occupy these one. If there is 1 electron here, that first electron would occupy the T2G. We also know that given a possibility or given a chance, then the dxy, dyz, dxz, since they are not along the axis, they are not facing the greater repulsion by the ligand, they are the first which are going to be occupied in the metal. Now, The next available orbital, this is therefore T2G is going to be what we are being here in the MOT is going to label it as lowest unoccupied molecular orbital, that is LUMO. LUMO short form is LUMO. So lowest, this is the HOMO, highest occupied molecular orbital, and this EG is going to be the lowest unoccupied molecular orbital. So this sort of the labeling is also necessary so as to understand T2G with the EG star. So d orbitals, dxy, dyz, dxz, they are going to accommodate the first of the 3 electrons, then the fourth and the fifth can enter into EG or can also get accommodated up to T2G6 configuration, as we have seen in case of CFT, where del O can be greater than P, then the low spin complex will be formed. When del O is less than P, then a high spin complex will be formed. That means this separation in energy level, once again like in CFT, is going to decide that whether the electron configuration in the various MOs will be T2G and EG followed by EG, singly occupation of T2G first, then EG, or it is going to be first T2G getting T2G6 configuration, that means all 6 electrons getting paired up here, and then the 7th entering into the EG. That also, once again, as we discussed in the CFT, becomes the basis for the order of filling of electrons. So here, if you look at the gap between the energy levels, up to the level of T2G, the electrons are going to occupy the order A1G would be filled first, then T1U, then EG. But in T2G, we have to see that whether the del O is greater than P or less than P. Based upon that, the distribution of electron in T2G and EG star would take place. Although in CFT, this doubly degenerate orbital was labeled as EG, but exactly or more precisely speaking, through the molecular orbital theory, this is antibonding molecular orbital EG that has resulted, and that quite understandable also, because they are going to be experiencing a greater energy repulsion. Now, based upon this, therefore, we can have for various complex ion situations where a sigma bond or a octahedral complex is formed, we can draw this energy level diagram, and the separation here becomes very, very important. This electronic configuration of D, how many number of electron? 1 electron, so T2G1, 2 electrons, T2G2, 3 electrons, T2G3, 4, then you can have 2 possibilities, like in CFT, we have dealt high spin and low spin situations, that is also being encountered in MOT. This becomes a simple diagram. Now, once again we understand that what sort of energy and what sort of symmetries would have allowed the ligand orbitals to overlap with the metal. It is not that all ligand orbitals can form a bond with the metal. You need to have them of equal energy or a comparable energy if not equal. You need to have the ligand orbitals with a symmetry that suits and the direction of their orientation that suits the overlap. And through this consideration, we say 6 orbitals of the ligand, 1 from each ligand containing lone pair of electrons, forms 6 symmetry adopted linear combination of orbitals termed as LGOs. So the ligands are not going to have the simple AOs situated on them. The ligands are going to have the LGOs, the ligating group orbitals. These ligating group orbitals may be formed because of the combination LCO of orbitals ultimately accommodating this electron density. The span of the irreducible representation is A1G, T1U and EG. If we apply group theory and try to have an idea that what sort of, in an octahedral complex, what sort of those orbitals, LGOs, that will be available for formation of the bonds or the overlap, then in that case it will be A1G, T1U and EG symmetries. And that is why you have seen that while we have drawn the MO, these are the symmetries A1G, T1U and EG. So these were of the coming from the metal, and these same symmetry, they were coming from the ligand. They have resulted into a constructive overlapping, forming these initial 6 MOs bonding, and then they are also resulted into a 6 antibonding situation T2Gp remaining the non-bonding situation. Now, the metal has 6 orbitals, where s orbitals labeled as A1G, 3 of the p they being labeled as T1U, and dz square and dx square minus square they are being labeled as Eg. So now you get a identical symmetry from the ligating orbitals, LGOs group, A1G, T1U and Eg, the same symmetry that is being available on the s, px, py, pz, that means the p orbitals, and dz square and dx square minus square, that is the Eg of the metal. So they have combined so as to form 6 plus 6, 6 bonding, 6 antibonding MOs. So 6 bonding MOs resulted from combination of LGOs with the metal orbitals of the same symmetry, and similarly 6 antibonding MOs has resulted. This LGO concept therefore is more important because we have to match the symmetry of the metal d orbital with the ligand orbitals. Unless it is done, you can't have a proper symmetry or a proper orientation of these orbitals in space so as to have a complex or a orbital overlap to take place and a complex to be formed. Now, similarly, if we apply the same criteria so as to explain what sort of energy level diagram that will get for tetrahedral complex, that also we need to see. Now, just look at the figure that I want to show. Now, this is the MO diagram for tetrahedral complex. Here metal is surrounded by 4 number of ligands so as to form Ml4 complex. Now, here instead of 6 as it was in octahedra, now we have 4. We are presuming it to be a D2 system so as to tell how electrons would be distributed. Now, since it is a reverse case, in a tetrahedral situation we have already noticed that it is the E set of orbitals, that is dx square minus y square and dz square, which are along axis, they are not going to be directly faced by the ligand's electron density. So they'll remain unperturbed. So now here E is going to form a non-bonding set of orbitals, which is doubly degenerate, not triply degenerate as it was in octahedral complex. Whereas the other, they are going to, that means the 3 of the d orbitals, they are going to form the bonding and the anti-bonding situation. Now, you can very well see from here we have got 3 combining with 3 here, 1 of the 4, that means they are combining with the S, and then the P here, Px, Py, Pz, that remains non-bonded. That remains, it comes into bonding and the anti-bonding situation, but that is an orbital which is now of a higher energy. Now, this particular energy level diagram is a clear-cut, has a clear-cut distinction from that of the ML6, that means the octahedral complex. Situation here is that we get a bonding T2 energy level diagram, then a singly degenerate level A1G, then we have the non-bonding E set, and then the T2. The difference between the E and the T2, now T2 actually is a part that is not coming from D. This is a distinction from that what we have observed for, but it is coming a part T2 here, and this T2 is combination of this and this. So they are being formed here, and then you have T2 star here also. So you have a situation where 4p and dxy, dyz and dxz, they are resulting into a differential energy level diagram where you have a bonding and a bonding situation where 4 ligands contributing 8 electrons, they are being get accommodated, and then the electrons from the D, they are being occupying E, and the next when there are 5 or more electrons, then it will be T2 that will also be occupied. But remember, delta T is always very small, so the pairing energy, it never gets exceeds 2, and hence it is the high spin situation. Even in the third electron in the D would be occupying into the T2 energy level, which is being here, and hence will have a almost identical result as that of a CFT, but in a differently obtained way. I mean, here the energy level diagram that we have obtained is maybe appearing to be similar if you concentrate to this part, but overall energy scenario, is also being discussed, and we are also being taken into consideration that while overlapping and while covalent bond formation, what energy changes the orbitals accommodating the electrons coming from the ligand they have undergone. So there is therefore this kind of a departure from the CFT to MOT has taken place. Hence we have underlined this, that this molecular orbital theory is more quantitative in nature, and it tells us a more precise energy variations that takes place when the ligand and the metal orbitals combine so as to form the bonds. Now, we cannot leave up to only those situations where a sigma bond has been formed. When the ligand approaches a metal, it is quite understandable that the AOs of the metal is going to interact with the electron density of a ligand. If it is a head-on overlap, a sigma bond results, that we all understand. But there can always be a possibility of a sideways overlapping of the other orbitals available on the ligand with that of the d orbitals of the metal. Head-on, let us say if we are taking an octahedral case, the head-on situation will be only for the dx square minus y square and dz square orbital. But electrons are also residing in dxy, dyz and dzxz orbitals. And if during the head-on overlap, sideways overlap is also being allowed or being possible, we cannot restrict it. They are there on the metal, they are there on the ligand, and along with the sigma bond formation, therefore a sideways overlapping resulting into a pi interaction will also be taking place. Even in the simplest of a complex like cobalt forming a complex with, let us say, 6 fluoride, you cannot ignore the possibility of the orbitals, p orbitals, which are not in the plane which is undergoing a overlap to form a sigma bond, or they are in a perpendicular plane, but still they are forming a bond, that means a sideways bond with the metal d orbital's electron density. So such a situation, therefore, is to be considered if we want to have a full idea about the energy changes that are taking place. Hence, pi bonding in MOT coordination compounds need to be considered along with the sigma bonding. Now, pi bonding in the octahedral complexes occur in various ways. One of them is that the p orbital that are not being used in the sigma bonding of the ligand, they form a overlap with the d orbital of the metal. This is one way of doing a pi bond or forming a sideways overlap. The other is the ligand may be having a pi or a pi star molecular orbital present on the ligand. That can also, because it is being perpendicular to the bond axis, so that can also undergo a overlap with the d orbitals which are also in a different plane. They can have a symmetry being allowed, the direction being allowed, maybe not head-on overlap, but a sideways overlap may result. That means, and this situation we have seen occurring in various various complex situations. The p orbital not being a part of sigma bonding, undergoing an overlap with the metal d orbital. Pi star, like in carbon monoxide, pi star undergoes a overlap with the metal d orbital so as to form a sideways pi bond. D orbitals on donor atoms like sulfur, phosphorus, the d orbital of the ligand can overlap with the d orbital with the same symmetry and this direction, or the same plane can overlap with the d orbital of the metal so as to form an additional bond to the sigma bond. And hence, pi interaction cannot be ruled out, and it is always being present. These are the normal 3 types that we have to consider. Now, pi interaction takes place with the appropriate d orbitals like dxy, dyz, dxz. This you need to remember. You cannot have a situation for octahedral complexes where dz square or dx square minus y square undergoing a pi interaction with the ligand orbitals. They will always be forming a non-bonding situation. So, pi bonding is to be considered. Now, as each of the 6 ligands, they have 2 pi bonds, the symmetry of the 12 in all, and what we have seen is that the symmetry adopted linear combination of these fall into triply generate irreducible representation of T2G symmetry. And what we have got is when the metal ligand pi bonding occurs, the LUMO of the ligand are antibonding pi star orbitals. These orbitals are close in energy to T2G orbitals, with which they combine to form the bonding orbitals. The orbitals of the lower than the T2G orbitals and the antibonding, they are the higher ones. So after pi interaction, there will be energy change. So though T2G and the EG, which was occupied in the MLC6, the sigma complex, when you consider the pi complexation, we understand T2G overlapping with a pi ligand, that means the pi interaction of the ligand which may be vacant. So this is getting lower in energy. So what it has resulted therefore is a greater separation between T2G bonding and the EG star antibonding. Now this situation, in fact, as I started considering the pi interaction, stronger pi interaction from the metal to the ligand, that means the electron is getting transferred from metal to the ligand, the del O value has increased. Now this is quite obvious because the electron charge which has increased, getting accumulated on the metal, has got a chance to back donate it towards the ligand and hence allowing the stronger bond formation with a greater separation between the two. Now similarly, we can have the other way around. If you look at this particular diagram, you will appreciate that this is an overall situation with the increased one. But there can be other way around also. That means when there is a ligand to metal pi bonding that has taken place, in such a scenario, what may happen is that the T2G having a pi interaction with the pi ligand filled ones, like in fluoride. So what it has resulted into a increase of T2G energy with the pi electron pi interaction being considered, and when it happens, del O value in fact is decreases. Now this therefore becomes a very straightforward answer, that how do for a ligand like fluoride, bromide, iodide, whenever we consider the pi interaction along with the sigma interaction, even though they have a negative charge present on them, the situation has come where the del O value has decreased, whereas whenever there is a transfer of electron density from metal to the ligand, then del O value increases. So the refinement in the molecular orbital energy level diagram needs to be carried out in view of such interactions, that is the pi interaction. So pi interaction therefore in short can have both effects, increase in del O value for ligands like carbon monoxide, for ligand like phosphenes, for ligand like which have pi star antibonding MOs which can back bond with the metal so as to accommodate the transfer of electron density from metal to the ligand, and in a reverse way, if it is from the ligand to the metal, already a sigma bond ligand to metal interaction, charge transfer is taking place, and then also along the pi bond, the ligand to the metal charge transfer taking place. This will decrease the energy between the energy of the two levels and hence have a smaller del O value. This differentiation is necessary to understand the pi interaction that has resulted into variation of energy. Thank you very much.
Dear friends, due to paucity of time, we have to stop our lecture here. On that note, we would like to thank Dr. Ajay Kumar Bhagi for coming here and delivering this wonderful lecture. And thank you, dear friends, for watching our lecture. Stay tuned and keep watching. Thank you.